Hello, everyone, and welcome to another Phenomenex webinar. Today, we will be going over understanding reverse phase selectivity for different compound classes. This is a method development approach. I'll give you guys a little bit of background while a few additional people come on in. So my name is Genevieve Hodson. I am the manager of the technical support team at Phenomenex. This is a global team and we help support our products everywhere all over the globe. So I've been with Phenomenex for about 6 years now. I've always been on this team, but before I was a method developer for many years and worked on a wide range of different analytes during my time. With that, I will go ahead and get started and we can move to the overview. If I do want to mention that I have Addison on the line as well, so if you guys do experience any problems or there's any problems with audio, he'll come on and let me know that there are problems with audio if I cut in or out. Also, he'll just let me know if things cut in and out. Just hang on and we'll fix it. So looking at an overview of today's presentation, there's a lot to get through today, so keep with me here. First, we're going to go over chromatographic resolution and selectivity relationship, the relationship between the two. Then we're going to go over some stationary phase characteristics, particle type, pore size, bonded ligands, and capping, specific selectivity. Then we'll jump into stationary phases and the selection based on different compound classes. So this would be hydrophobicity, methylene selectivity, steric selectivity, aromaticity, hydrogen bond donating capacity, hydrogen bond accepting capacity, cation selectivity at different pHs, specific applications, and then finally, we'll talk about mobile phase selectivity, which sometimes gets a little bit overlooked. Oops. So we'll jump into chromatographic resolution and the selectivity relationship. So again, the purpose of chromatography is to resolve individual compounds in a sample from each other. And this is the resolution, the primary goal. So resolution is a measure of how well the two individual compounds or peaks are separated from each other. And it's calculated as the difference of retention time of the two eluting peaks divided by the average width of the two peaks at the baseline. So resolution is presented and calculated through this equation here, right? Resolution is primarily affected by 3 different factors. This is efficiency, which is represented through theoretical plates and peak asymmetry. Then you have selectivity, which is controlled through the mobile phase and stationary phase, which we'll be talking primarily about today. And then you also have the retention factor, which is dependent on mobile phase, the ratio of mobile phase, column dimensions, particle size, and some other characteristics. Here on this chart, right, you can see that although peak capacity or retention factor and efficiency do impact the resolution greatly at the beginning, selectivity continues to impact the resolution of methods long after the efficiency and retention factors become stagnant, basically. So looking at a little tree here, right? We look at selectivity, and I said that it was based on mobile phase and stationary phase. So here you can see when we look at stationary phase, this boils down to type of phase and either hydrophobic phases, C18, C8, C4, polar modified phases, which we'll talk about later, phenyl phases, biphenyl, PFP. And then you look at the mobile phase part of the selectivity. This comes down to buffer, pH, organic solvents, other additives, the type of buffer, concentration of the buffer. So there are a lot of different things that are playing into the overall selectivity of a method. Now we'll move on into phase characteristics, stationary phase characteristics. The first thing that we're going to be talking about is particle type. So there are kind of mainly 4 to 5 different types of particles based on the backbone of the stationary phase, right? And we're going to be mainly talking about silica-based particles and silica-based medias here, not polymeric, although that is an option. There are other different particle types or media types. So on these, right, you have fully porous silica, you have thermally modified fully porous silica, so silica that's undergone a thermal modification. Then you have monolithic silica rods. You also have follicular or core shell silica that has a solid core and a porous shell. And then finally you have fully porous or core shell, but mainly this is organosilica or hybrid particles. So that could either be hybrid fully porous or a hybrid core shell, right? So both of those. Going on to this, there are different advantages and disadvantages of each of the different particle types, right? So one of the main differences between core shell and fully porous is the mass transfer terms of the two different particle types, right? So with fully porous particles, these don't optimize or favor fast kinetics. And this is due to the resistance of mass transfer and band broadening can occur in a fully porous particle compared to core shell particles where there is less resistance to mass transfer. There's overall less band broadening, which then results in sharper peaks, better efficiency as well, and increased sensitivity of analytes. That's not the only advantage of core shell. Another advantage to like better peak shape and better efficiency is that you can run these at a higher linear velocity because of the lower back pressure that they have. So you can run them much faster, save solvent, save analysis time as well. Although fully porous silica does have its place, you can load more onto fully porous silica because there is more surface area for the analytes of interest to interact with the silica and the phase. So you can load on more of your mixture, your sample onto fully porous particles compared to core shell. So everything has its advantages and disadvantages, right? Looking at the particle types, again, we're going to be talking about silica, primarily silica, although we will talk about organosilica. So silica gel, looking at this equation down here, silica gel is manufactured under alkaline conditions through polymerization. That word always trips me up, polymerization. So this is done under alkaline conditions. Again, it is unfortunately a reversible reaction, and this can be reversed when the silica is exposed to those alkaline conditions again, which can cause the silica particles to then dissolve. And that's why most conventional silica particles have a max pH of 7.5 or 8, right? So if you go above that pH, then you start to begin to dissolve these silicas, and it's the siloxane bridge that begins to break down. So to combat that and provide another option as a different particle type, there are hybrid particles out there that have been invented, right? So these are organosilica particles or hybrid particles where the siloxane bridge, right, that is normally the weak point, has been replaced with an ethane linkage. And that ethane linkage is more resistant to pH, right? It doesn't break down during that alkaline pH. So you can run them at much higher pH ranges without having to worry about the siloxane bridges breaking down and dissolving the silica. Moving into pore size and porosity. So the pore size of a stationary phase is sometimes overlooked when it comes to chromatographic analysis. Generally, we go with the notion that a smaller pore size is suitable for smaller molecules, where a larger pore size is required for larger molecules, which isn't wrong, right? But there should be some consideration given to the pore size and porosity of the silica that you use when you are doing method development. So as we know, surface area and porosity of a particle are interdependent. Important to note that here, usually the particles that have smaller pores have larger specific surface area, but the surface area of 1 gram of particle also depends on the number of pores there are in that particle. And that's what is considered porosity. So there can be a particle having a small number of pores, but only a very small pore, but a small number of those pores, and therefore will have a small specific area, compared to a particle with more pores, which would have a higher porosity, even if those are small pores. So the larger the surface area of the small pore silica stationary phase, it will provide more retention and more resolution for smaller molecules compared to larger pore sizes. But again, the larger pore sizes are needed for larger analytes. So analytes should have at least 10 to 15 times larger pore diameter to ensure that the mass transfer is fast into and out of the silica particle for efficient interaction with the stationary phase. That's key, right? Now looking at the types of bonds that are out there, right? So these are classical bonded ligands. So when it comes to reverse phase chromatography, there are primarily alkyl and phenyl bonded ligands, which are used in most analyses, although there can be other ligands like amino and cyano. Those are a little bit more limited, right? Those are options. So for alkyl ligands, these include different types of like C18, C12, C8, C4 ligands. There's also C30, C5, even C1 ligands that can be used in reverse phase mode. And then below we have an example of the different types that these ligands can be bonded onto the octadecyl silane. So how different examples of how the octadecyl silane C18 ligand can be bonded onto the silica. This is usually done with primary bonding. That's when the ligand is bonded on. So first we have a conventional monofunctional C18 that is bonded onto the silica, right? Then we have a difunctional silane. So this double attachment here is thought to increase the stability of the ligand and lower the pH, and therefore kind of lower the phase bleed that can happen, you can see. Then you can also do trifunctional silanes, right? So you can do a C18 or a ligand bonded to trifunctional silanes. So this one, it can be done. Again, it could help use lower pH values and decrease the bleed, but they're harder to manufacture reproducibly. So they tend not to be used because they are more variable, right, from batch to batch. Then we also have sterically protected. So this would be, sterically protected or bulky silanes, right, where an isopropyl or isobutyl group can hinder the siloxane linkage or bridges from hydrolytic cleavage at lower pHs. And then finally, we have bridged or cross-linked phases. So this is where a bidentate organosilane is grafted onto the silica particle, which can better shield the surface from dissolution at the higher pHs. This bridging or cross-linking technology can be extended from one to several protective organic and inorganic layers, right? So depending, that would result on different stability of the phase. However, this cross-linking should not be confused with a full hybrid silica particle, where the organic moiety is the main component of the particle construction and not just on the surface of the particle. So here we're talking about not alkyl but phenyl ligands, right? So you have phenyl ligands as a complementary selectivity to alkyl ligands that were shown on the previous slide. Primarily, the bond is aromatic, hydrophobic, and some electrostatic interactions that these provide. Some of them provide also steric and isometric selectivity, or can provide. Here we have the visual of a PFP or an F5 phase that can interact in 5 different ways. So it can interact aromatically, hydrophobically, sterically, electrostatically, and it can also have hydrogen bonding. So it can offer a bunch of different ways to interact with the analytes of interest. Here we have different specific selectivities. So these can again be complementary selectivity to alkyl and phenyl ligands. These are polar and mixed mode ligands, right? So an alkyl bonded stationary phase primarily separates a compound based on hydrophobic interactions. However, these alkyl stationary phases can also have polar embedded or polar in-cap groups, which can impart a polar selectivity to the column along with the hydrophobic selectivity of the main ligand that's already there, the C18, C8, right? So the last figure shows an alkyl chain, much like a C18 counterpart, but this one has a polar group intrinsic to the chain. So this could either be an amide, urea, carbamate, right? These polar embedded groups have led to a new class of phases that offer surface silanol shielding and additional polar retention. So these are polar embedded, right? So the polar embedded moiety yields good peak shape towards basic analytes and makes the phase compatible in 100% aqueous conditions without the de-wetting or hydrophobic collapse that can happen. However, these polar embedded phases can change the sequence from using just a C18 to then going to a polar embedded, right? It can change the selectivity, can change the sequence or retention order of the method that you're looking at. Finally, looking at in-capping, right? So in-capping, what does this mean? So free silanols are inherently acidic in nature. So these are, these have a pKa of 3.5 to 4.5. And again, free silanols are any of the silanols that are left over after the primary ligand. So after the C18 or whatever ligand is being used, phase is being used. So they're left over, unbonded after that, right? So these isolated silanols are especially reactive towards basic compounds and can affect by doing a lot of tailing. So controlling and maintaining the abundance of these residual silanols is critical to making sure that you have the peak shape for your basic compounds. And in-capping can be done to help reduce this. So in-capping is a secondary bonding, and it's used to cover any of these free residual silanols after the primary bonding. So the in-capping ligand can be either hydrophobic or hydrophilic. A common one is TMS or trimethylsilane that's used. That's the most common. So they can either be hydrophobic or hydrophilic, and they will affect the overall selectivity of a stationary phase. So a polar in-capped group can impart that unique selectivity to classically bonded C18 ligands, and at the same time, they can maintain their structural, their fundamental hydrophobic selectivity. So stopping quickly and giving a break to a quick poll question. So I just wanted to quickly know which area, since we're talking about method development, which area do you find most confusing when, or frustrating, confusing when developing a new method? Is it choosing a phase? Is it choosing a column dimension? Is it choosing what buffer, maybe the concentration of the buffer, or which one, what pH to work at? Is it picking the gradient or isocratic conditions, or is it something else, right? So just wondering what you guys find most frustrating or confusing, or you have a hard time starting, right, when working on a new method. So I'll let you guys answer that. So it sounds like choosing a phase might be the most difficult for you guys, and that's great. You guys are in the right area, right? So we're going to be talking about the stationary phases next. So we'll move on to stationary phase selection. So this is stationary phase selection on the basis of compound classes. So I'm going to be talking about the different types of compounds that you could be looking at. So it's not just about the phase, but it's kind of in context with what compounds they would be good using or working with. So stationary phases and their selection parameters. The first one is hydrophobicity. So this is the ability of a stationary phase to hydrophobically interact with the carbon groups on the analyte. The next one is methylene selectivity. So this is the hydrophobic character of a C18 phase that allows it to readily discriminate between molecules based on subtle hydrophobic differences or a methylene group. Then there's steric selectivity. So this is the ability of a phase to separate compounds based on structural differences. And then there's aromaticity. So this is stationary phases that contain a ring structure that can interact with a aromatic or ring-containing compound via pi-pi interactions. Then you have, then you also have hydrogen bond donating capacity. So this is the ability of a stationary phase to form hydrogen bonds with proton accepting groups such as oxygen or halogens, halogen-containing compounds. Then you have hydrogen bonding accepting capacity. So this is the ability of a stationary phase to form a hydrogen bond with a proton donating group such as hydroxyl or amine containing compounds. And then finally, we have cation selectivity. So this is the ability of a phase to interact with a cationic group or cationic groups on the compound either at pH 2.8 or at pH 7.0. So two different options for pH there. So when you look at these different stationary phases, right, you can kind of, skipped ahead, I think. There we go, step one. It's important to start at the right step, right? So here are a few of the different selection steps that you can take to pick a good phase to start with, right? And that will impact your selectivity. So step one is identify the functional groups and the chemical differences between the compounds or the analytes that you're looking to separate. So if you have a lot of different analytes in a method, right, you could look at some of the main differences between the analytes, or if there is one, you've already tried a column and there's one critical analyte pair that you're not able to separate because they are too closely related, then you could focus on that critical pair. So it is a little trickier the more analytes that you add, right? But usually there's a sticking point. You know, there's a few that you're having problems with, and we'll go through the examples and you'll see kind of there's pretty good separation, and there are a few analytes of interest where there's struggle. So here, right, we have a second degree alkyl that is metabolized into an ether. So these are the two analytes that we're trying to separate here. And here is the difference between the two compounds. The rest of the analyte is consistent, right? So step two is relate that chemical difference to a type of interaction. So you're going to correlate the differences between the analytes to stationary phase selectivity that we just talked about, and we'll continue to talk about. So here with the alkyl, or the alkyl, excuse me, we have a hydrogen bond accepting capacity, right? So we're looking for a hydrogen bond accepting capacity in our stationary phase. And then here we are looking for hydrophobicity, right? We're focusing on this methyl group right here, and we're looking at the hydrophobicity. So those are the two things that we're going to focus in on. And then step 3 is select an appropriate column selectivity from the differences that you've identified. So you want to choose a stationary phase with selectivity for the related categories. So here we're going to choose one that has a strong hydrophobicity and it provides hydrogen bond accepting capacity. So you'll notice here that there's lower steric interaction, hydrogen bond donating capacity, cation, and then also missing here is aromaticity as well. That's missing off of this chart, but usually is included. So these are typically included on the charts. And I will say that Phenomenex, we have these on most all of our columns. We have them. Usually in the brochures, you can find them. Also, many column vendors have these kind of selectivity charts based on really similar guidelines. So they're out there, right? So then if you were looking at a drug and a metabolite, you would then have a successful separation of those two analytes, right? Because you've chosen something that has that will offer different interactions for the different analytes that you're trying to separate. So looking at hydrophobic selectivity and kind of going through each of these, right? A selectivity tip for hydrophobicity is that the partition coefficient, or the log P, measures a compound's hydrophobicity, right, and can help predict an analyte's potential to interact hydrophobically. So it's a good kind of point to work from. So here we have an example of a hydrophobic selectivity being used. This is being used with non-polar neutral steroids. So we have a kinetics polar C18 at the top, so it's a C18 ligand, and then a C8 at the bottom. And here, right, so we are having trouble separating 8 and 9, and we need a stronger interaction for hydrophobicity in order to separate these compounds. So when we change from a C8 to a C18, then that longer alkyl chain provides more hydrophobic interactions, and we can finally get separation of those two analytes. Another example is lysosome. So this is looking at larger molecules. So an example with larger analytes of interest using alkyl ligands. So at the top we have a C8, and these are both wide pore, right? So usually above 200 angstroms is the pore size. So on the top we have a C8, and on the bottom we have a C18. So we're trying to get some separation out here, and we're trying to pull out as much as we can. And so here with the C8, we're getting some resolution that's being lost, but when we go to a C18, we're then able to get that resolution. Next, we're going to be looking at, let's see, I think I have a question. Apologies. Apologies about that. So methylene selectivity is the next one that we're going to be looking at. So a selectivity tip here is stationary phases with longer alkyl ligands, C18, and higher carbon loads will provide better methylene selectivities. An example of methylene selectivity, so here we have testosterone and methyl testosterone. The difference between the two is a methyl group. So there's no other difference but the addition of one methyl group. So you can see with an F5, right, it does have some hydrophobicity that it does provide. So there is a little bit of separation. We go to a C8 and there's a little bit more, but finally at a C18, it has a higher methylene selectivity that it offers because it has a longer alkyl chain and a higher carbon load than the other two, and that results in the best separation or resolution between the two analytes of interest. Then going to a steric selectivity. So a selectivity to here, high bonded surface coverage and high surface area, both on C8 and C12 ligands, and of course phenyl stationary phases provide the highest steric selectivity. So those are the phases that we think of when we think of needing a steric selectivity. So an example of steric selectivity, here we're looking at different, we're looking at a 5-phenyl, a C18, and an F5, 5C18 and 5-phenyl. So we're looking at methoxybenzene isomers, and you can see 3 of the isomers here. We didn't list all of them, but the F5 will give planar and steric differences where the kinetic C8 won't. So you just see one peak for the 3 analytes. The kinetics biphenyl provides a little bit of the steric separation or steric selectivity, right? But the F5 by far provides the most separation or resolution between the analytes that these 2 analytes really have the same, I mean, they're isomers, right? So they have the same chemical formula. It's just really their shape that's different. Aromatic selectivity. So this aromaticity is the aromatic selectivity is a transient attraction between 2 aromatic rings, and this results from subsequent alignment of the positive and negative electrostatic potentials of the aromatic rings. A tip here is to use methanol for the organic portion of the mobile phase if you're looking for this selectivity, because it can help promote pi-pi interactions, where the acetonitrile, on the other hand, competes for the analytes pi-pi interactions. So it'll start competing with the stationary phase, and then you're not going to get the kind of retention or selectivity that you want if you're focusing on this type of selectivity, right? And with that said, I realized that in this example, I've used acetonitrile. Doesn't mean that you cannot use it. We have endoprofen and ethylparaben, and on the first one, where we just have a C8 ligand up here, and then on the bottom, we have a C18. This is a polar embedded group right here. So this is a polar embedded alkyl column. And again, we have this additional aromatic selectivity that's given here when compared to a C8. Looking at hydrogen bond donating capacity, so non-ionized bases and compounds with electron withdrawing groups such as oxygen or halogen containing compounds might require this selectivity, or it would be a good choice, this type of selectivity. So non-ionized bases and halogens or oxygen containing groups on different analytes of interest. An example of that here, right? We have a lot of different compounds of interest, and we have 2 different hydrogen bond donating capacities. So on the bottom for the kinetics of 5, we have a lower selectivity, so this is not contributing as much as the cation selectivity, right? On the top, we have a higher amount of hydrogen bond donating capacity. So if we're looking at using this hydrogen bond donating capacity as the selectivity that we would like to use to separate some analytes of interest, so say we have 4 and 7, which is, let's see, phenyl and thymine, I always pronounce that wrong, and then 11 and 12, nortriptyline and 5-MSA. So we're having a hard time separating these on the F5. So when we move to a polar C18 that has a higher hydrogen bond donating capacity we can then get the separation that's needed. Although you will notice that there are some changes in the elution order, right? 7 goes from being right here to pushed back, and 12 is also being retained differently. So this is an example of you have a group of analytes that you're trying to separate. You're going to focus on hydrophobicity, right? You maybe try something like kinetics F5 that has 5 different modes of selectivity. You try that one, it doesn't work, right? You need a little bit something else for different compounds. You look at those compounds, you look at the differences in the functional group, and then you go back and choose a column that has a higher selectivity that you need. Now looking at hydrogen bond accepting capacity. This one is for compounds that contain hydroxyl or amine groups that can donate protons and can interact through hydrogen bonds with the stationary phase, which can accept it. So these hydrogen bond interactions can take place additionally with silanols, polar in-cap groups, or polar ligands, and can be utilized to manipulate the selectivity and gain retention and resolution of these compounds, these hydroxyl and amine functional group containing compounds. This is especially true for highly polar compounds, and which you'll see in the examples. So here's an example of polar basic neurotransmitters. Again, we need additional retention of these analytes, and so we're going to choose a phase. So we started off with a C18 phase. We were just trying to get as much hydrophobic interaction that we could and enough retention that way, but it didn't work, and we need some additional retention. So, we're going to try and keep the hydrophobicity still high, but then choose hydrogen bond accepting capacity since these are very polar analytes. So then we'll go to hydrogen bond accepting capacity and this Luna Omega polar C18, which has a polar modified surface and a C18 ligand, does provide that selectivity for us. Finally, we're going to look at cation selectivity at 2 different pHs, 2.8 and 7.0, right? So stationary phases, which have a high cationic selectivity value, will show higher retention for ionized bases. Now note that that's not neutral bases necessarily, but ionized bases. Stationary phases which have low cation selectivity values, although they have less interaction and retention for ionized bases, they may give better peak shape due to electrostatic repulsion, right? This is extremely useful to retain 4 compounds longer and in order to move them away from the void or from early ion suppression region if you're working with mass spec. Here's an example of this. So we have basic and neutral drugs of abuse, and we have it on first. We tried a C18. Right? We have a large amount of different analytes that we're looking at. So we go to C18 first. We see if we can get some retention there. However, we're not getting great retention for our basic drugs of abuse, right? So we're going to try a different phase while our neutral drugs of abuse are getting relatively good retention. So we're going to try and change things up. And since we're working at a lower pH, right? So you can see here we're working at a lower pH with formic acid in water and methanol. So that's why we're focusing on the 2.8 pH. So we're going to be looking for a cation selectivity that has a higher value. And with the kinetics biphenyl, we do have that. And you'll see that there's been, some changes in elution order, right, or retention times, and that the neutral ones are still being retained, right, but now we're pulling these other ones along with it. Another application, we're looking at, one moment. So for this application, we're looking at polar acidic compounds. And here we have two different stationary phases. We have one with a positively charged surface. So this one, the silica itself, has a positive charge that's integrated into it, and then a C18 ligand with traditional TMS end-capping or non-polar end-capping. Then we also have a polar modified silica as well, and that's integrated into the silica, and it has the same ligand and same end-capping. So really, we're working with a positive charge or a polar charge. And you can see that the Luna Omega PSC18 for the polar acidic compounds, it has an ionic interaction and it is able to improve that resolution. Finally, looking at a specific application, here we're looking at high pH selectivity. So our Gemini column has a hybrid particle. So this is an organosilica hybrid particle. And again, these are stable to a higher pH when compared to a phenyl. And with that, we are able to run at a higher pH and have stable reaction. And we can see additional retention when our analytes of interest are in their neutral form. And we can get additional retention of those analytes when compared to just a traditional phenyl column. So a final poll question for you guys to stop before we talk about mobile phases. This one is, would you or do you want to be contacted for help with your method or your application? So yes, I could use some support, or no thanks, I've got it under control. So just quickly, we'll go through that poll question and we'll move on. Okay, moving on, we are going to be talking about mobile phase selectivity, which is our last section in today's webinar. So in reverse phase chromatography, to achieve the goal of resolution of the analytes and good peak shape, hydrophobic and some electrostatic interactions play a big role in that selectivity. To achieve that goal, the primary objective of a chemist should be to get the desired analyte of interest into a single state. So you don't want both the deprotonated or unionized state and the neutral state of the ion both present at the same time. Because the ionization state of an analyte directly affects the interaction of that analyte with the stationary phase. So pH is the factor that directly controls the ionization state of the analyte or analytes. Therefore, to understand the true significance of pH in mobile phase, we first need to understand the degree of ionization or the degree of dissociation of an acidic and basic molecule. The pH of the compound can indicate whether you're dealing with the acid or the base, right? And it offers limited information indicating the true strength of that acid or the base. And that comes with the concept of degree of ionization or dissociation. The higher the degree of ionization, the stronger the acid or base. Analyte ionization is indicated by pKa or pKb values, and therefore the stronger the acid, its pKa value will be smaller, and the stronger the base, the larger you would expect the pKa value to be. All compounds can be analyzed, all compounds that can be analyzed by reverse phase chromatography can be at least slightly ionized. Thus, they can either be weak acid or weak base. Therefore, when working with such polar compounds, you always should know the pKa or pKb of the compounds of interest because it'll help you decide the correct pH for the mobile phase. Now, I understand you guys were saying that you struggle the most with phase and stationary phase, but mobile phase selectivity does have a big impact as well on the retention of the analytes. So there are always challenges that come with analytes that are partially ionized polar compounds through reverse phase chromatography. When a molecule is ionized, it is more polar and therefore more likely to participate in hydrogen bonding. In reverse phase with aqueous mobile phase, the analyte will spend less time in hydrophobic interactions with the stationary phase and more time forming that hydrogen bonds with the aqueous part of the mobile phase. That's compared to when that molecule is neutral. So it'll result in less retention of that polar analyte. When there are significant concentrations of both ionized and neutral forms of the analyte, so here the acid is 50% dissociated or the base is 50% dissociated, the ionized form will have less hydrophobic interactions while the neutral form will have more hydrophobic interactions, which will result in kind of a pulling apart and result in broadening of the peaks or asymmetrical peaks. There are, again, right, the free silanol groups or metal contaminants present in silica may participate in ionic interactions with the ionized state of the analytes. This could lead to poor peak shape or reproducibility issues as well. And so to control the ionized state of the analyte, you should control the pH of your mobile phase. This can be done with buffers or additives, right? So what you're going to be looking for is a pH equal to, when you're working with an acid, you ideally want it to be 2 pH units below the pKa of the acid, right? So you're going to do pKa -2, and that's the pH that you should work with. So the analyte will be mostly neutral. For basic compounds, you want 2 pH units above the analyte of interest, right, or the pKa of interest. And ideally, right, if you're working with a number of different compounds, you can't get all of them into a neutral or ionized state. So what you want to do is just make sure that you're not at the exact pKa or pKb of one of your analytes, because then you'll see broadening happen. So if you're working with a lot of molecules and you can't target one specifically, right, then make sure that you're really not at the exact pH of any of the pKas, because you don't want to have that dual species present. And speaking about dual species and what we're talking about, right, here's an example of the different pKas and what impact that has. So here we have aminoacidic acid or glycine. This has both conjugate acid and base, right? So it's got 2 isoelectric points. It's got one at 2.3, or yeah, 2.3, and then a basic one at 9.2, right? And from pH of 4 to 8, roughly 4 to 8, you have a single species distribution, but it's sort of ionic. So you're not able to have it neutral, right? But here, where you're going to have your acid neutralized, right? So your acid will be neutralized, but you will have an ionized form of your base, right? And then here you'll have both charges present. And then at the higher pH, you'll have your base be neutralized, but then your acid is now ionized as well. So these charts can be very helpful in picking a pH to work with. And ideally, again, you don't want to work at this pKa and this pKb, right? These are the ones that you want to avoid, and you really want to avoid 2 pH units above and below that, right? So 2 pH units above and below that, because you see that they're drastically changing. Looking at the effect of pH on retention, here we are using a column of capable of low and high pHs, and we see in red examples of these basic compounds at low pH, and in blue we see the difference of these basic compounds when they're run with a high pH. In this case, it's 10 millimolar ammonium bicarbonate in water. So you can see that for all of these basic compounds, right, they are getting higher retentions or additional retention when run at their neutral state, and they're able to retain on the column longer when compared to an acidic state, right? And here you can see their log P's. These are pretty polar analytes right off the start, right? Looking again at the effect of high aqueous in mobile phase. So I had mentioned that there are columns that can withstand 100% water or 100% buffer without having phase collapse, and there are those columns that cannot. And the ones that tend to be able to have this resistance to de-wetting or phase collapse are the ones that have polar end caps or have polar embedded groups. So here, right, we're able to run at 100% aqueous conditions, and we get additional retention of ETG and ETS, whereas with a normal C18 that doesn't have any polar groups, we're only able to run the highest 97% buffer, and that's really, really, it's maybe not the best reproducible method with 3% methanol here, but it is an option, and you don't really get as good retention, and you don't get the separation that you need. So looking at the mobile phase selectivity, the buffers are added again into the mobile phase to control and maintain the pH. These are selected based on their buffering capacity and their specific pH range. The buffering capacity is the ability of that buffer to resist change in pH, and it's usually directly proportional to the molar concentration of the buffer salt and its corresponding acid or base. So buffer selection depends on the desired pH of the mobile phase, which in turn depends on the pKa values of the analytes of interest, or the ones that are giving problems. Thus, ideally, you should choose a buffer which has its pKa value close, within 2 pH units of the mobile phase that the pH of the mobile phase that you're using. The buffer should always be compatible with the detector. That's an important thing not to forget, right? Buffers or additives used with mass spec should always be volatile. So ammonium salts, formic acid, ditriethylamine are most common additives. And when you look at UV vis, right, you need to use a buffer. You need to use a buffer that has a lower UV absorbance or UV wavelength, right? Because then it could start to begin to interfere with the analytes of interest. And then finally, the solubility of the buffer is important, not just as in the aqueous, but also in the corresponding organic. If you tend to use too high of a percentage of organic, sometimes the buffer can crash out of the aqueous, and then it will start to crash out onto your column, which is not great. So looking at mobile phase selectivity and looking at the strength of different solvents, right? So we look at acetonitrile and methanol, which are commonly used in reverse phase chromatography, and we can look at their strength and also their selectivity difference. So here is a run on a C18 column. It's run with the same mobile phase, or it's run with the same aqueous, so water with 0.1% formic acid, and then in the blue is methanol, and in the orange is acetonitrile, and you can see that acetonitrile is considered a stronger solvent, which means that it has it will elute the analytes of interest quicker with less that is needed. And then you can see with methanol, right, so it will elute later. So there is a difference there. And then you can also see that there is a difference in selectivity as well, right? So the peaks are kind of changing their order, I believe, yeah. So 6, 4, 5, right? Whereas this is 5, 6, 7. So they are changing their selectivity as well, just by changing the organic solvent. Then finally, looking at the effect of ion pair reagents. So ion pair reagents can be added to your method when working with a C18 column most commonly, and these can add additional retention based on like ionic interactions, right? So the sample contains no ion pairing reagents in the mobile phase, and then it's run with the ion pairing reagent. And also the amount of ion pairing reagent can also impact the retention. So 0.05 and then 0.2% octyl amine. So the different strengths can also impact the resolution. So it's important to be clear about what concentration of ion pairing reagent you need to be adding, because the retention time can shift based on that. And with that, I will go into the summary of what we talked about today. So we talked about hydrophobic compounds, hydrophobic selectivity with alkyl ligands, C18 and C8. We talked about aromatic compounds, aromatic selectivity with phenyl ligands, so phenylhexyl, biphenyl, F5. Then we talked about compounds with similar size and shape, high bonded surface coverage, high surface stationary phases like C8 and C12. Right? Then we talked about steric selectivity and positional isomers. So this is PFP, the stationary phase can be utilized there. Then for unionized bases or oxygen and halogen containing compounds, these you should look at hydrogen bond donating stationary phases. And then for hydroxyl and amine containing compounds, then look at hydrogen bond accepting stationary phases. For polar bases, look at a cation selectivity or utilizing cation selectivity, stationary phase that has that. Then for polar acids, polar selectivity or mixed mode anion exchange stationary phases like the PS-C18 or positive surface C18 or the F5 that has the 5 different modes of interaction. And then for polar bases and alkaline mobile phases, polar bases you can use a high pH mobile phase. You would need an organosilica hybrid like a Gemini or an Evo if you're looking at our different phases, although there are a number of organosilica or hybrid columns out there. So with that, if you have any questions or you need the assistance of a method developer, we have my team, staff, our chat. So you can chat with one of our technical specialists. This is my team. This is a team that I manage, and we can help with chromatographic inquiries. You can help chat with method optimizations, product recommendations. We have sales people on there as well that can provide quotes for purchasing. But if you want a mind to bounce ideas off of, right, another method developer to bounce ideas off of, what phase might be good, what mobile phase to try, these are my analytes of, that I've been struggling with. Come and chat with us. And then finally, thank you for your time and your attention. Again, my name is Genevieve Hodson. I'm the manager of the technical support team here at Phenomenex. Here is my contact information. But if you want to get a hold of a method developer quickest, use our chat because they're there all the time. So with that, again, thank you for your attention today. And I made it right in 1 hour. So I hope you guys have a wonderful rest of your day, and thank you for joining.